So hello, everybody. I am delighted to welcome you to today's News from the Lab event, and I'm sure you are all excited to learn more about the current state of the art in terms of machine learning on quantum computers in the context of high-energy physics. My name is Simona Kriba, and I work at the CERN Alumni Office, and today I'm joined by two amazing guests, CERN alum Yuri Anderson, who will be moderating today's session, and our speaker, Dr. Sofia Vallecorsa. And before we jump in, just a couple of words also about our moderator. So Yuri is a serial entrepreneur with 20 years of experience as a scientist, manager, director, and investor. He has founded and co-founded a number of deep technology startups, and currently he is the CEO of cybersecurity company Angoka. And besides that, he holds a number of other chair, board, and executive positions. So many thanks, Yuri, also to you for accepting our invitation, and I shall now leave it up to you to introduce our speaker.
Thanks so much, Simona. My pleasure to be here. And it's even a greater pleasure to introduce Dr. Sofia Vallecorsa, who started out at Sapienza in Rome before going to University of Geneva to do a PhD, although she spent most of her time at Fermilab at the CDF experiment. After that, after completing her PhD, she went to do a postdoc stint at Technion in Haifa in Israel, and after which she joined CERN, initially at the Atlas experiment, before going on to join CERN Open Lab. And this is really where she started working on quantum machine learning within the simulation group of Open Lab, collaborating with industry partners to develop quantum machine learning solutions as a way to improve simulation. And she's also the coordinator for quantum computing activities within the CERN Quantum Technologies Initiative. So I'm really excited and looking forward to hear what Sophia has to say about this very exciting topic of quantum machine learning. Sophia, over to you.
Thanks, Yuri. So I'm very happy to be here. I'm going to share right away my screen, and you'll please confirm that you can see it fine.
All good.
You do. All good. Great. So I will indeed talk about quantum machine learning and the work we're doing about that at CERN. But I wanted to give this talk a slightly more general context, and that's why you're seeing here quantum computing at CERN. I'm not sure how much you know about the Quantum Technology Initiative. We started at CERN a couple of years ago, so I will also talk a bit about that. I think it's important to put everything in context. So let me start right away with some sort of, you can look at this as an introduction or as a conclusion to the slide, as you prefer. But I wanted to make this a few points clear right at the beginning, so that, you know, even if we run out of time, at least I'm sure that you get all the major point I wanted to make. So the first thing is, of course, the fact that, yes, quantum computing is a very lively field of research. On a daily basis, basically, you can see new applications and use cases that are studied, and solutions to different problems, more and more realistic, are being proposed. Together at the same time with a lot of work that goes on from a more theoretical point of view, right, with attention to really understanding the behavior of those systems. At the same time, it is also true that we cannot think of replacing today classical classical computing with the quantum one, at least for large-scale problems, as any data analysis problem we have at CERN, for example. So this is a longer term, I would say, goal, for which, however, we need to start, research with quite some advance, well ahead of time. And why am I saying this? Today, most of the limitations that we have are somehow related to hardware. What we call the near-term hardware is a noisy environment, it's made up of unstable systems, and this has an effect on the size of the problems that we can think of solving with the quantum computing, on the complexity of the algorithms that we can implement, and on how stable and unstable the results are. So that it sounds, I would say, kind of a, a negative approach to this, but it really isn't, because what I'm saying is that while we do have strong limitations today, at the same time we have opportunities to also drive research and improve on the, I would say the path towards better hardware in the future. Okay, so this is something that we really strongly believe in, the aspect of co-development, the aspect of looking really at how studying the performance of algorithms on specific applications can also have an effect on improving solutions at hardware and software levels. It's something that has already happened in the past in other fields, and it's going to play a major role also in quantum computing. This is general. In addition, I would say that CERN is in the position of investigating a field, the field of high energy physics, that is naturally, I would say, suited for this kind of studies, because it is true, if we are looking into data analysis, and so understanding the measurements of our detectors, we are talking about understanding classical data. But at the same time, this classical data is generated, or let's say is somehow still related to the quantum process that generated it originally. Okay, so it is quantum in nature. So because of this, taking all of this into account, the Quantum Technology Initiative was created. Officially, it started a little bit earlier, I would say, but officially launched in September 2020. We also developed a roadmap, which is available on the Zenodo platform. It's actually been accessed more than 5,000 times. I checked, I didn't update the slides. I mean, more than 6,000 times, so I didn't update those slides recently. Together with computing, the initiative covers a broader area of investigation, which, so as Yuri mentioned, I'm coordinating the computing and algorithms part, but there are branches related to sensing. So understanding how quantum technology can improve detectors, and this specifically, so I will not talk about this, but it's another very important, I would say, aspect, really complementary to what we do in computing, because it's really trying to understand how we could use, for example, for very low energy experiments, how to introduce quantum sensors in there. Then there is a part about theory and simulation. This is more related to using quantum computing to do direct simulation of physics processes, and at the same time to understand how to improve theoretical calculations, how to also bring in directly quantum information principle. And then there is also an area that it's more related to quantum communication and networks. And now this is probably not directly related to what we do daily at CERN. At the same time, CERN has been for some years already part of the QKD network, the quantum key distribution networks, and we even had a dedicated project that tested how to implement a full data analysis framework, or more than framework, I would say, workload on a distributed network through quantum key distribution. So before going directly into, or more specifically in what CERN does, let me just say a few words of about quantum computing as a hype. This is something that comes up very often. It's often actually the first thing people that don't work in the area know about quantum computing, something that's either very big and it's going to solve all our problems, or something that will die out very quickly. I would say that it is true there have been in the past few years big announcements. I quote here the Google announcement on quantum supremacy in 2019, and then just shortly after, similar results that was published by the Hi-Fi National Lab in China. So those were very, very also controversial kind of announcements. In the case of Google, for example, just a few months after there were publications and discussions and proofs that actually all the benchmarks that were had run on the classical side of the experiment were actually not that correct. I'm not sure how much you remember, or if you took notice of this kind of announcement in the past, but basically what Google showed was that they could solve on their system a sampling problem that supercomputer centers such as the Oak Ridge, the one present at Oak Ridge, would take I don't know, hundreds of thousands of years to solve. Okay, so effectively unsolvable at the classical level. But this turned out not to be the case. However, what I wanted to really stress at this point, and which I think it's very important, that's important in particular for our quantum program at CERN, is the fact that those kind of announcements were really focused on problems that don't really have that much of an application today in a realistic field. What we are interested in is more understanding what quantum computing can do in problems we have, in daily problems, in problems that originate from our scientific environment. And this is not only, I would say, a research perspective. What you see on the right, on the right, I think, if you can see my mouse moving, it's an example. There's a few of those studies that exist, but this is an example from one consulting company, McKinsey, that shows what is the expected impact that quantum computing could have in the business sector according to different fields. You can see finance, healthcare, and so on, over a shorter time scale and a longer one. Whereby short, well, they call it actually medium, it's 2025, so a few years from now, and longer term is not that long because 2035 it's slightly more than 10 years for now. So I think this gives a good overview of how people are looking at this field. Why is that? What is the idea behind quantum computing? The idea behind it is using quantum effects basically to improve algorithms to solve problems that we cannot easily solve classically. Okay, now I should specify each one of the objectives I put in this sentence. So when we say quantum, I guess your CERN alumni, I shouldn't bother explaining what quantum effects are, but here in this case, we are specifically talking about the entanglement and superpositions. For computing, those are two of the things of the effects that play major roles. And when I say improving algorithms, what I mean is either accelerating those, so reaching solutions over a shorter amount of time, or really improving in the sense of getting to a better accuracy or a better results. Okay, and there are different examples. Some of those algorithms have already been studied for quite some time, have been known and designed for quite some time. Grover's and Shor are examples of this. You've probably heard about them already. Quantum Fourier transforms also exist as a relatively, I would say, established approach. Anything that has to do with linear algebra, it's also algorithms that can be accelerated using quantum computers, and therefore the interest towards quantum machine learning. Although I will talk more about this. Quantum machine learning, it's interesting because we are not just looking, for many reasons, and we're not just looking at speeding up an algorithm. We are looking at models that could have better representational power, so able of learning more complex distribution with respect to the classical one, basically. Then there are also, and I mentioned it briefly here, but I will not talk about that further in this talk. It's the idea of what are called quantum-inspired algorithms. This is also a very vague or relatively vague definition, but what I mean by that here is just the idea of emulating a quantum effect on classical hardware. This is the case, for example, when we talk about quantum Monte Carlo methodologies for optimization. Now, whenever we talk about these algorithms, I would say that the most important or the biggest challenge there is the fact that beyond designing the algorithm itself, what we need to be able to do, what we need to understand is how we can recast our problem in a way that is suitable for quantum computers to work on it. Okay, this is absolutely not straightforward. I would say the typical initial approach would be to try and solve a problem by translating, okay, on a quantum circuit, something that we know how to do classically. This can work, but it usually doesn't yield the best result. Okay, so the difficulty in this kind of research is really at the level of rethinking how to solve a problem. And of course, there is a big discussion about what it actually means to do a fair comparison to classical algorithms. Okay, now this is particularly true when we are talking about quantum machine learning, because on the classical side, we don't have, I would say, an established or clear way of measuring metrics for a lot of problems. Okay, in particular when we are talking about generative models. So this is tricky. So whenever we discuss about comparison to classical methods, we need to clearly say what it is that we're doing. This is just an example of applications in high energy physics that have been published in the past few years. There is a lot already, actually. These are not based on quantum machine learning. As a general, I would say, if I had to identify a few general categories, I would say that anything that has to do with Monte Carlo and simulation and event generation is likely a topic that a field that could profit from quantum computing. Quantum simulation, for example, simulating lattice QCD problems. Pattern recognition, so very different kind of approach, but anything that has to solve large combinatorial problems, this is something that can profit from quantum algorithms as well, and of course quantum implementations for machine learning. I would like to stress that here, when I talk about quantum machine learning, I will talk about using quantum computers to improve machine learning algorithms, but there is also a different kind of research that's related to using machine learning to improve quantum systems, or understand how they work. For example, using variational methods to model noise and errors on quantum systems. Okay, so these are things that exist. I will not discuss those here. The examples that you see, I picked those two because they show two very different applications. The top example is really, it's called the quantum associative memory application to a problem of tracking. This is very similar to the idea of using associative memories in the classical domain when you want to do when you want to reconstruct a particle trajectory, for example. What you can do is to create a database of pre-paired trajectories, and then whenever you get your set of hits, you can just compare to each one of those until you find the right one. And this is basically, this is a very simple description of the method. Of course, it's not so simple. It's not so, not so simple, but it gives you an idea, and then you can clearly see what it means if you can do the same implementation on a quantum system where the data, when you can leverage exponential compression for your data through the superposition principle. If you have a system with n qubits, then you can represent 2 to the n classical bits. Okay, so this is clearly visible in problems like quantum associative memory. So this work that I'm showing you here, and the bottom plot, the bottom part of the slide instead is showing you an example application for the simulation of parton showers. So this is another this is a topic that is particularly interesting also because it can be very heavy in terms of computational resources classically. So proving that quantum systems can actually do this with a similar accuracy is it's very good. Now, I briefly mentioned that today quantum computers are far from perfect. This is not just a problem of number of qubits. It's a problem of what is the connectivity with them, what is the topology that you can actually implement. Usually, what happens, on a quantum computers, you can design your algorithm, so you can design the different operations that happen at a single, 2, 3 qubits level. But then there will be a moment similar to the compilation step in the classical world where your code, your circuit will be adapted to the real connectivity and real topology of the qubits network on the system, qubits graph on the system. And this can become very, very cumbersome. You can end up with very complex circuits that can have a worse performance, or let's say that can suffer more of the presence of from the presence of errors. So those errors originate. There's different kinds. We don't need to go into the details of this, but let's say that overall they naturally originate from the fact that we're talking about quantum states, and therefore there is a coherence time that is finite. There are, of course, error mitigation techniques. There are ways to optimize circuits. And there are algorithms that are more robust to noise than others. And quantum machine learning is indeed one of those algorithms. Because quantum machine learning systems, because quantum, because I would say, let's say generically quantum neural network, then we will see what it means. But let's say, because since those are trainable, so they learn iteratively over time, they can also learn noise while they learn their task. Okay, the task. So this is something that ends up with a relatively that works with very little problems with respect to noise. I'm simplifying. Of course, there are cases if the networks are particularly complex in which we need to take into account of a phenomenon that's called barren plateaus. This is well known. I don't know, many of you are interested in classical deep learning, I would say. That's a problem that exists also in the quantum implementations of those systems. So the idea, the fact of ending up in the optimization space in regions in which the gradients don't change anymore, basically, and therefore it is impossible to train the model. It becomes impossible to train the model. Another aspect that I wanted to stress at this point, and it's typical of, let's say, near-term devices, is the fact that we are seeing today that most of the quantum systems are being implemented or integrated as, I would say, accelerators within larger classical computing infrastructure, within cloud environments, for example, or HPC centers. This is, it's very, I would say, it's good in the sense that it allows us also to develop algorithms that are hybrid, and therefore introduce quantum circuit in a way that is gradual, okay, within our workloads. So specifically at CERN, I said quantum computing is one of our 4 research areas, and I also said that we are interested in applied research. So we are interested in understanding quantum computing for our own applications. So our main goal is really understanding what use case could profit from a quantum implementation the most. Okay, to do so, we started by choosing representative use cases. You will see basically they cover the whole spectrum of the data processing chain in our experiment. We've chosen use cases for which we do have a classical solution, because what we want to do is really to understand the challenges and the limitations that are related to quantum implementations. Okay, and of course, the focus for now is not exclusively, but strongly, I would say, on quantum machine learning. This is for the reasons that I mentioned before. It's they can be implemented easily as hybrid models, they are robust to noise, and they can be very generic algorithms, right? So if you make them work for a specific use case, you can adjust it and then solve a lot of different problems. Now, of course, quantum machine learning algorithms have I would say, an aspect that it's very important and very tricky when you try to do the implementation on a quantum computer, and it's a fact that's really, and it's the challenge related to data handling. Typically, a classical machine learning or deep learning algorithms performs best on large data sets. And today, this is a big limitation for a quantum implementation. Okay, so this is something that should be stressed right away. And before going to the algorithms themselves, I also wanted to mention that CERN has joined also the IBM Quantum Network as a hub. It means that we have access to IBM hardware with a certain quotas, and we can have members that can join our hub. And this is something that for now is limited to 3 years. But we have already created a small hub with which includes INFN and the IIT. So the Italian Institute for Technology, if we can translate that like that in English. And the idea is really to join forces on understanding how quantum computing works on physics use cases, but also chemistry and biochemistry, which is the expertise that comes from IIT. Okay, so quantum machine learning. I said briefly, I used the word quantum neural networks. Right now, there are two main ways of defining a quantum machine learning algorithm. The two most popular, I would say, that go back basically to the same dichotomy, if we can say that in English, that exists in the classical machine learning world, which is basically neural network versus kernel method. In the quantum domain, we talk about variational algorithms versus kernel methods. The idea in both cases is that quantum circuits are differentiable. And so we can think of training them by minimizing a cost function, okay? That will depend on the data. We can define optimizers that can calculate gradients and therefore drive the training towards some cost function minimum, basically. Now, variational algorithms are something that actually go beyond quantum machine learning, but in this case, you can really think of them as neural networks, okay? Parametric circuits in which the parameters are trainable, okay? So if you look at the sketch that you see here at the bottom, typically you would train a variational algorithm as by initializing a quantum system, embedding, so loading your data set after some preprocessing pipeline that is extremely important, and I will talk about it in a moment, in a quantum state, defining the variational circuit targeted to some specific task, for example, a classification task, running the circuit, measuring the results, and then running a classical optimization loop. So basically building a loss function, calculating the gradients, and updating the weights in the quantum circuit and repeating. Okay, so if you think about it, this is very close to what happens in the classical world with neural networks. The other option is to take a kernel-based approach, and this in the quantum domain comes naturally, because when I talked about embedding classical data on a quantum circuit, what I actually meant was to build a sort of feature map. And what we can do is to interpret this feature map as a kernel that is simply mapping our data points from the classical space to the Hilbert space on the quantum system. Okay, and then once we've done that, then we can use basically all the typical, I would say, structures of not structures. I'm sorry. I would say strategies that are used in a standard kernel-based optimization. So leverage the fact, for example, that our losses are convex. So there is a single global minimum that exists And this is a big advantage, for example, with respect to neural networks, okay, where the chances of ending up in local minima exist, I would say. Let's say it that way. And so the disadvantage with using kernel methods is computationally they are more expensive. So training a kernel method can be longer in terms of iteration than variational algorithms, because you need to build kernels or calculate kernels for couples of points. But okay, this is another discussion. We don't need to add that now. There is actually also, I will not spend time, but I would like you to be aware of the fact that there is a lot of research that is trying to link the two representation, and that is trying to understand how they can, what are the regime in which we can map one to the other, and what are the advantages in terms of accuracy and generalization with respect to using one approach or the other. Now, I mentioned data handling, and I mentioned data processing, data pre-processing chain. Now, again, I don't know how many of you worked on machine learning and deep learning. One of the things that I would say very happy about when I moved from machine learning to deep learning methodologies was the fact that I could really give up a lot of this very sometimes very complex feature engineering steps, okay, that were typical of the machine learning approach. Now, this somehow is something that is coming back. I mean, it got back its importance, okay, because of the situation with the current with near-term devices, basically, okay, because we need to be able to reduce the dimensionality of our data sets to sizes that we can easily embed in our current hardware. What we also need to do is to try and optimize this processing step, okay, and there are different ways of doing this. They can be completely classical, they can be fixed, like principal component analysis, they can be trainable. What we've actually seen is that the choice of the data preprocessing step can have a very strong effect on the performance of the quantum part of the algorithm, and actually training those two steps together in a hybrid setup usually yields the best results. Yeah, there's this discussion. The last part of the slide there is about the discussion of what does it mean. This connects to what I said before about what it means to actually look for an advantage when you are trying to define, when you're working with quantum machine learning algorithms. What you want to do is to end up with quantum algorithms that you could not efficiently simulate classically. But of course, this does not automatically apply to any kind of data sets, okay? So there are studies that you can do to try and understand from a geometrical point of view, more information theory related point of view, what is the potential related to that specific use case. And this is something that we started to do recently, sorry. We actually discussed this today too. We are going to have a paper about this out soon. And just as an example, these slides collect a few examples, a few use cases or applications. I would say they do not come from CERN only. Actually, I tried to get collect here examples of applications that the community worked on, just to show you that this is not just a CERN initiative. There is a lot of work ongoing in understanding quantum computing for high energy physics everywhere, basically. You can see examples everywhere and on very different tasks. So you can see, for example, here this top left example shows how you can use you can define a quantum classifier to do bit tagging, so to understand if the jet that the detector, if the measured or observed jet was originated by a B quark. You can define autoencoders to do anomaly detection. You can define classifiers to do a binary classification in a typical, signal to background classification problem when you are really looking at the high-level features in your analysis. There are two examples here. You can use, you can define also, this was also a similar use case classification problem, which used a completely different quantum technology. So typically what you will see in most of the work I show you is about uses digital computers. In this case, this is the, I would say, the update of one of the probably the very first work that presented quantum computing for high energy physics, which used the quantum annealer. And here you see quantum implementation for convolutional neural networks. At CERN, we have a little bit of a similar situation. Also, specifically, CERN looked into a lot of different problems. You can see here at the bottom, this is the application to track reconstruction. Okay, this analysis built the equivalent of a graph neural network. So use the graph representation for the data point and then build a quantum classifier to reconstruct particle trajectories. Here you see an example of a reinforcement learning problem applied to beam optimization. Then we have a generative model example, actually two of them, they are here, that use, so the idea in these two cases is to generate the event generation. So choose a physics process and generate the output features of a set of particles. And those two examples are very interesting because they use two very different models to do that. One is called a quantum born machine. I will tell you a little bit about it in a minute. And then another one is a hybrid implementation of a generative adversarial network, which is one of the most popular, I would say, classical deep generative models. On top, here you have another example of classifiers. You have another example of this is an anomaly detection that uses a clustering algorithm. This is another problem of event generation. I think what's shown here, I don't know if I'll have time to give you more details about this plot, but I just wanted to mention, this is a study that shows how noise, this uses a classical simulator for the quantum system and studies how the noise is affecting the convergence of a GAN, of a generative adversarial network, because we really wanted to understand if a model in a noisy environment will converge over a longer period of time and to which accuracy. And if we don't get there, I'll tell you right away that we're very happy, because up to very large amount of noise, basically we see that the model can recover, so it can converge to the desired accuracy. So let me tell you, I forgot, when did we start? I forgot to keep time. I think I still have like 5 minutes, huh? Something like that. Yes, 5 minutes. Okay, thanks. Thanks, Yuri. So yeah, I mentioned the problem of event generation. What's interesting about this model is the fact that the quantum circuit board machine is a generative model that does not have a classical counterpart. So when I talked before about the fact that what's really interesting is going beyond, classical algorithms and trying to leverage directly from scratch, I would say, quantum effect, I meant designing algorithms like this one. What does a born machine do? So when you train a born machine, what you're doing is training a quantum state to reproduce probability distribution function, and then you can leverage directly the Born rule that you see expressed here. That that you can reproduce through the measurement process. So you can use this process to directly sample from the probability distribution. Okay, so this is just a direct application of the Born rule. So conceptually, it's very simple, linear, very nice. There are, of course, also in this case, nothing is perfect. There are limitations. So far, for example, we were able to use it to only generate discrete probability distribution. So, for example, as in this case, if you want to generate the energy of a particle that is produced in some scattering problem, then what you need to do is to discretize it. And of course, this is a limitation in a realistic environment, right, where you would like to have a very good representation of your spectrum. But it works, and it works also. What you see here is a comparison of the behavior that we observe for the Born machine when we train it on simulators, when we train it on real hardware. So this means that the systems are stable, and our simulation of the system is it's correct. I will not go through these examples. And I just wanted to show you the reinforcement learning problem, which is here, because this allows me to make a couple of points. So this example is something we worked on in collaboration with the colleagues in the CERN accelerators department. So the use case, it's a relatively simple, where we started with something relatively simple. So one-dimensional problem, the steering of a particle beam towards a target. So you can see it represented here. Basically your state, if you're I'm not sure if you're familiar with the reinforcement learning, but the idea behind reinforcement learning, this is a technique in which you train an agent to reach to learn the best possible policy, so to provide the best possible action towards some goal through continuous feedback with the environment. Okay, so this is a loop in which your agent tries with an action to modify some state, and it receives back some reward from the interaction with the environment. And in our case, we model our action as the deflection angle, the state measured by some position monitor, and the target. The reward is basically the overlap between our beam and the target distribution. And this is a problem that you can solve with classically, of course. The approach we chose is a deep Q-learning approach, in which the reward function is represented by a feed-forward neural network. So that is the baseline. What we did was to replace this classical network with a Boltzmann machine, so with a quantum neural network that also in this case is trained on an annealer. And what we find is that our quantum system can have although it's much smaller, because we are talking about a network that has an order, you can see it here at the bottom, that has an order of 50 parameters, can reach the optimality in a number of training steps, which is maybe, I don't know, a factor 300 smaller than the classical one. And I would like to point out that, of course, this is a very simple problem, but we took care of actually optimizing the DQN, the classical network, to the solution. Okay. We actually moved on beyond this. We were happy with the results for this DQN from this DQN approach. And so we made something more complex. We changed the reinforcement learning setup, and we train now the agent in an actor-critic situation, or let's say setup, in which the critic is quantum. What happens in this case is that this is if you're familiar with generative adversarial network, this is a very similar setup for training a network. Okay, the goal here is to train the actor, and the actor is a classical network. And the quantum computer is, so the quantum implementation, the QBM, is used basically to accelerate the training of the classical network. Because of this, since the actor is a classical network, what we can do is to use it today. Okay, we don't need to bring the quantum computer close to our beam lines in order to use it to steer the beams in the accelerators. Because once the actor is trained, then that can be deployed as any other network would. And indeed, our colleagues tested it on a real beamline. This is the awake electron beamline, which is a 10-dimensional problem. Okay, the beam position in the accelerator is measured 10 times, and we were really happy to see that the system actually worked, in spite of the fact that one of the monitors was off, or I mean, it had a problem, and so we had one less measurement to rely on. And so to conclude, well, let me see. I said most of this already before at the beginning of the talk. I don't want to say more, but what I want to say is that we spent most of the time at CERN so far to really try and understand how those algorithms work. Now we are really trying to see instead what workflows could be improved by using quantum computers. So this is really the focus for the next couple of years. And this is something that we want to do over a short term, so taking into account the characteristics of the near-term devices, but also over longer term. So what will happen, what will be feasible once we have access to fault-tolerant computers. And well, this is just, I mean, it's a very complex slide. I just wanted to show you, this is an example of a roadmap. This is the IBM roadmap that shows that already in 2023, they expected to deliver us order 1,000 qubits systems. Okay, so this also gives you an idea of what is the potential that industry is seeing in this, how far they think they can go in the next few years. Thank you.
Absolutely fascinating. Thank you so much, Sophia. We've got a couple of questions here on the chat. I've got one from Giordano. His question is, when I think about quantum computers, the semiconductor industry comes to mind. How are quantum computers produced today, and how do you see the future development be? And if I may add a question to that, I'd be interested to get your take on hardware platforms in general. You mentioned that there's always going to be some issues with the compilation aspect into the actual hardware that runs these quantum algorithms. Do you see that there are any particular platforms that are better suited for quantum machine learning?
Two good questions. So let me say, I don't want to talk about which platform is best, okay, or works better than others. I think we're still at the level in which there is a lot of research that is ongoing, and it's not clear what is the most promising technique. Now, it's true that most of the I would say results that we see around, and most of also the in general, the research is towards semiconducting devices. They've been known, or let's say they've been investigated for a long time, so they're certainly like a relatively or more stable technology. There is also a lot of research on ion traps. So a device that we can access today that uses these technologies is, for example, IonQ. Now, this kind of devices have different features. Okay, so for example, you can have different level of noise that you can expect, whether you are using a semiconductor technology or an ion based technology. There are different levels of connectivity between the qubits that you can have in the two cases. So at that point, it's really a matter of what are the requirements for your application. Okay, so we are still not at a level in which we can say, okay, it's better, we should use ions instead of semiconductors. In fact, there are just two examples. There's much more. There is, for example, photonics-based quantum computers that are so basically you use the quantum states you use for building your algorithms is a collection of photons. Okay, so there the kind of operations that you can implement is very different. The way you represent your data is also very different. For example, a big advantage of photonics is the fact that you can reproduce continuous variables. So this can have a big impact, for example, on all the work I showed you so far, right? Everything I showed you is discretized. If you want to increase the resolution of your distributions, you need to increase the number of qubits. But instead, if you can directly represent them as continuous variables, that is a much more direct, I would say, advantage that you can get to. So it really depends. Now, for quantum machine learning, I think, again, the way we define this today, so for example, the quantum annealer is a machine that is already very, very stable, and we have thousands of qubits. For the use case that I showed you, we just use a few tens. Okay, so this is a small portion of it. But the problem with quantum annealers, or let's say not really a problem, it's a limitation, that it is meant to solve specific problems. So like optimization problems can run easily on an annealer. If you want to run different tasks, then you need to try to formulate it as an optimization problem. It's not always possible. But for example, quantum machine learning is something that can leverage quantum annealers very, very well. But also, I would say at this stage, all of them, we should keep trying using all of them. Yeah.
Thank you. There was a question from Yanis, who was asking, what is the size limitation for neural networks on today's quantum computers? So how many nodes can a network have?
Okay, yeah, that also depends very much. So there's different things. There are different issues here. There's the limitation that's related to the number of qubits that you want to use. So something that is related to the hardware itself, number of qubits and how deep that is. So I would say that reasonable use cases today don't go beyond some maybe 20 qubits, let's say less than 50, and circuits that are no more than I don't know, 80, 100 gates deep, even less. Okay, so this is the size, and this is more related to it has an effect. I mean, it's related more to the hardware. But what I mentioned at some point at the beginning of the talk about the existence of the problem of barren plateau is very relevant in this case, because by increasing it has been proven already, I think, if I remember correctly, the paper, this was a paper published initially, the first discussion about this was done by Google authors in 2018, and they showed that the variance of the gradients in the neural network, quantum neural network training decreases exponentially with the number of qubits. So the more you train, the larger the systems you try to train, the more you can run into a problem of barren plateaus. So this is something that also, of course, then has an effect on the choice of the network.
Great, thank you. I had a question around the interplay between the data and the running of the algorithms. And I just read a paper that came out quite recently from the Google team around using quantum sensors as part of the input into your quantum algorithms. And they claim that there should be some advantage to that. How do you see the chain of events happening when you're analyzing, for example, you're analyzing quantum systems at CERN? Could quantum sensors give you an advantage and then feeding into quantum algorithms?
Okay, so I don't know this paper. Please forward it to me, because I think it's extremely interesting. So one of the things is that I also briefly mentioned this at the beginning. All of the use cases you see here are use cases in which we are using quantum systems or quantum machine learning algorithms to learn or to analyze classical data. Okay, so there is likely only, let's say, there are limitations to the kind of advantage you can expect. Okay, it can be, again, as I said, in an additional representational power in the quantum system. It can be a matter of how fast it trains, as you saw for the reinforcement learning case. But at the end of the day, you can always think of designing a deep learning method, classical deep learning method, that's going to reach similar performances, right? So that is kind of the limitation that we have when we use those systems to analyze classical data. Now, the idea of analyzing quantum data has always been there. The problem is that it is possible only in very specific cases. So the idea of using quantum sensors that output directly as input to a quantum processing system, it's great, and it's something that could certainly make bring big changes. And it's also something that could be relevant to us. I mean, now I'm drifting towards not science fictions, but I would say really blue sky, right? You can imagine you could design a quantum sensors for our detectors and match it with some sort of quantum chip that could do your real-time processing directly there, and then just this would be I think great. Of course, we are far from there, so I want to read what Google claims. I think it's very, very interesting.
I'll send you the link. Simona, do we have time for one final question?
Sure, even two if you want.
Okay, all right. I wanted to go back to some of the things you mentioned initially around the hype versus reality. Now, of course, people in the industry are a bit allergic to quantum supremacy terminology and all that. But if we look at quantum advantage in the field where you work, what does that look like, and when do you think that we will get to that point? I know you showed the IBM roadmap, but in your opinion, how long will it take for us to get there?
Again, I think for us the problem is really also like defining this advantage, right? Because there are, for example, a lot of applications on the more theory domain in which the limitation today is the number of qubits. So the size of a lattice that you can accurately simulate is related to the number of qubits or let's say the size of the quantum system you have access to. So if indeed in a few years we will get to, let me get back to this, like let's say again, I chose the IBM roadmap as an example, but if we are talking about, well, let's say that beyond 2026, of course, beyond, we don't know what it means, right? But they're talking about order 10,000, 100,000 qubits. If that really happens, then that is something that will certainly bring an advantage in anything that's related to this kind of applications, for example, but also QML. At that point, we will have no problem in using a digital quantum system for simulating or studying continuous variables, for example. And it's not only, again, the size and connectivity and quality of the qubits, but what's happening, it's also the fact that there are, let's say, there's development in the way you can use those chips. So what doesn't really, maybe it's not so clear from this plot, but it's the fact that, for example, we are starting to see the possibility of parallelizing circuits within a chip, okay? So that opens up, or across chips. So that opens up a possibility for a lot more workloads or algorithms to implement. So I don't want to give you a time scale because I think it's really connected to this. If this time scale is true, then if this roadmap is realistic, then this is also a roadmap towards advantage.
Fantastic. No, that's excellent. I don't have any more questions unless there are questions from the audience. Maybe one last chance to get something in quickly.
I would like to ask a question.
Yep.
I'm sorry, I cannot have a camera. I was wondering, so you were saying that you were now, like these algorithms for stuff that you were doing on a quantum computer, but what are you using? Are you using the IBM devices for now, or where were you actually running your algorithms?
Yeah, so most of the examples that you saw, that you saw because that I showed are run on IBM, but not only. So if I go back here, I didn't put it, but we've run, for example, on IBM on the D-Wave, so the quantum annealer. We've run on IonQ. In the community, there are tests on different on Rigetti, for example. So in some cases, you can access those directly through the their company cloud system, cloud environment. In other cases, they are already integrated as services in broader cloud providers like AWS, for example. They have a bracket, which is a quantum system, and you can access Rigetti, IonQ, and other. Microsoft has something similar. So this starts to be not yet really a commodity, but not so difficult to access.
I guess all that I'd love to say is a huge thanks to both of you for the fascinating talk and amazing discussion. Thanks to all of you for all your time. We wish you a wonderful evening, and we hope to see you on alumni.cern.